Have you ever wondered why your steaming hot coffee eventually cools down? Or maybe why food cooks so much faster in a microwave oven than a traditional one? It all comes down to the invisible, but powerful science of energy on the move. Today, we're taking a deep dive into heat transfer and its fundamental concepts. It's a field that doesn't just tell us how much energy moves, but crucially, how fast. And this deep dive is custom tailored for you, designed to cut through the complexity and deliver core insights, surprising facts, and, well, practical applications that impact everything from your home to your own body.
And right off the bat, we should probably clarify what heat actually means here, because, we use it casually all the time. But in physics, it's defined very specifically. It's the transfer of energy that happens because of a temperature difference.
Okay, so that temperature difference is the essential driving force.
Exactly. Without that difference, there's no net heat transfer. Simple as that.
So it's why a cold drink warms up if you leave it out,
Hmm.
and a hot one cools down in the fridge. And the whole process stops only when the temperatures equalize.
Right. Precisely. That initial imbalance is what gets the energy moving. And this actually leads us to a really crucial distinction. It's the difference between thermodynamics and heat transfer.
Okay.
Thermodynamics, well, it's mostly about the amount of heat transferred when a system goes from one stable state to another. So it can tell you, for instance, how much total heat leaves your coffee as it cools from, say, 90 degrees Celsius down to 80.
Right, like the total energy change.
Yeah.
But if thermodynamics gives us the before and after picture, how do we figure out how quickly that happens?
Well, that's exactly where heat transfer comes in. It focuses entirely on the rate of that transfer, so heat moving per unit of time. And this distinction is absolutely vital in engineering,
Right.
whether you're designing, I don't know, a high-performance heat exchanger for a power plant or just trying to make a better thermos bottle.
So this means heat transfer deals with systems that are actively changing. Systems that are not in equilibrium, like that cooling coffee example.
Exactly. It's a non-equilibrium phenomenon.
Yep.
And the bigger that temperature difference, the higher the rate of heat transfer.
It's like voltage driving electric current, isn't it? Or pressure driving fluid flow.
That's a great analogy. That driving force, the temperature difference, is key. And if we zoom out a bit, heat transfer isn't just some, abstract concept for engineers. It's fundamental to our daily lives.
How so?
Well, think about our own bodies. We're constantly regulating heat with our surroundings. Human comfort is directly linked to how quickly we lose or gain heat.
Which is why we wear different clothes depending on the weather. We're managing our own heat transfer.
Precisely. And you'll find these principles everywhere in your home. Your stove, your air conditioner, the fridge, even your computer.
They all rely on managing heat transfer.
Right. Energy-efficient homes, car radiators, solar panels, even spacecraft design, it all hinges on understanding this stuff.
It even helps decide how thick the insulation in your walls should be to save money on heating bills.
Absolutely. And what's really kind of surprising is how our basic understanding of what heat is has changed so dramatically over time. For centuries, people had a totally different idea.
You mean the caloric theory?
Exactly. Proposed by Antoine Lavoisier back in 1789.
Right, the idea that heat was this invisible, massless fluid called caloric.
Yeah, like you could pour it from a hot object to a cold one. And it explains some things. I mean, we still use terms today like saturated liquid that actually came from that theory.
But it had problems, didn't it? Like, if heat was a substance, how could you keep generating it just by rubbing your hands together? Where's the caloric coming from?
That was the big question. Benjamin Thompson, Count Rumford, he challenged it back in 1798 with observations from cannon boring.
But it took a while to overturn it.
It did. It was really James Joule's careful experiments in the 1840s that sealed the deal. He showed pretty conclusively that heat wasn't a substance, but a form of energy.
Energy associated with the random motion of atoms and molecules.
Exactly. Not some magical fluid.
Okay, so now we know why heat moves, because of temperature differences, and it being a form of energy. So the next question is how?
Right. And there are three fundamental ways, or modes, that heat gets transferred: conduction, convection, and radiation.
And all three still need that temperature difference to kick things off.
Always. Let's start with conduction. This is basically energy transfer through direct interaction between particles.
So, like in liquids and gases, it's molecules bumping into each other.
Pretty much. Collisions and diffusion. In solids, it's a bit different. It involves vibrations in the material structure, the lattice, and also energy carried by free electrons, especially in metals.
Like when a metal spoon gets hot, if you leave it in a cup of tea, the heat conducts up the handle.
Perfect example. And the rate of conduction depends heavily on the material itself. We measure this with something called thermal conductivity, usually represented by K.
So a high K value means it's a good conductor.
Yep. Iron, for instance, has a thermal conductivity over 100 times greater than water.
Which is why a metal pot heats up way faster than the water inside it.
Right. Although, interestingly, water is very good at storing thermal energy, even if it doesn't conduct it quickly. And here's something fascinating about conductivity. Pure metals, like copper, are fantastic conductors. But if you add just a tiny bit of another metal to make an alloy,
Like making steel from iron.
exactly, even adding just 1% chrome to iron to make a type of steel significantly lowers its thermal conductivity compared to pure iron.
Huh. That's interesting. So alloys are generally worse conductors than pure metals.
Usually, yes. It disrupts the pathways for heat flow, both the lattice vibrations and the electron movement.
Okay, so conductivity tells us how well heat moves through a material. But there's another factor, right? How quickly the heat actually penetrates or spreads.
You're thinking of thermal diffusivity, often symbolized by alpha. This tells you how fast heat diffuses through a material. It's basically the ratio of how quickly heat is conducted versus how much heat is stored per unit volume.
So materials with high diffusivity heat up quickly throughout.
Exactly. Silver, for example, has a thermal diffusivity over 1,000 times higher than water. Heat spreads through silver incredibly fast.
This explains something maybe, like why if you step from a carpet onto a tile floor in winter, the tile feels so much colder, even if they're the same room temperature.
Absolutely perfect example. The tile has much higher thermal conductivity and diffusivity than the carpet, so it pulls heat away from your foot much, much faster. It feels colder because it's better at conducting heat away from you, not because its temperature is lower.
Got it. So let's make this concrete. Think about a house roof, maybe made of concrete. Say it's 6 meters by 8 meters and 25 centimeters thick.
Okay.
If the inside surface is 15 degrees Celsius and the outside is only 4 degrees Celsius on a cold night, say for 10 hours, how much heat are we losing?
Okay, with concrete having a typical thermal conductivity, you could calculate that loss. It works out to about 1.7 kilowatts continuously flowing out through that roof.
1.7 kilowatts, just through the roof.
Yep. And over those 10 hours, that adds up. Depending on electricity costs, that single night might cost the homeowner, say, $1.35 just from heat leaking out via conduction through the roof.
Wow, it really adds up. Okay, so that's conduction, direct contact. What happens when fluids, like air or water, get involved and start moving?
Now you're talking about convection. Convection is essentially conduction, but it's significantly enhanced because the fluid itself is moving.
So the fluid carries the heat along with it.
Exactly. If you use a fan to cool yourself, that's blowing air past your skin. That's forced convection. The fan forces the fluid motion.
And if the fluid moves on its own, like warm air rising from a radiator,
That's natural convection, or sometimes called free convection. It happens because heating the fluid changes its density, making it rise, while cooler, denser fluid sinks. This creates natural circulation currents.
does boiling water count as convection?
It does. Even processes involving a phase change, like boiling where vapor bubbles rise, or condensation where liquid droplets fall, are generally classified under convection because there's significant fluid motion involved.
And how do we calculate the rate of convection? Is there something like thermal conductivity?
Sort of. We often use Newton's law of cooling, which involves a convection heat transfer coefficient, usually denoted by H. But here's the tricky part. H isn't a simple property of the fluid like conductivity is for a solid.
Oh, what does it depend on then?
It depends on many things. The surface geometry, the nature of the fluid flow, is it smooth or turbulent? The fluid properties, and importantly, the bulk fluid velocity. It's much more complex to determine than K.
Okay, an example might help, like cooling electronics.
Sure. Imagine an electrical wire. Maybe it's hot, say 152 degrees Celsius, sitting in a room where the air is 15 degrees. If we know the wire's size and that it's losing, say, 90 watts of power.
We could figure out the convection coefficient H.
Exactly. Ignoring radiation for a moment, we could calculate H. And engineers do this all the time to design effective cooling systems, making sure components don't overheat.
Okay, conduction through contact, convection with fluid motion. What's the third way?
The third mode is radiation, and this one's quite different.
Yep.
Radiation is energy emitted by matter in the form of electromagnetic waves, or photons. It's a result of changes in the electronic configurations of atoms or molecules.
And the key thing is,
Yeah.
it doesn't need a medium, right?
Exactly. That's the most unique part. It can travel through a vacuum. This is how the sun's energy reaches Earth across the vast emptiness of space. Conduction and convection need stuff to travel through. Radiation doesn't.
So anything with a temperature emits radiation.
Anything above absolute zero temperature emits thermal radiation. The hotter it is, the more it radiates.
Is there a way to calculate the maximum possible radiation?
Yes, the maximum rate is from an idealized object called a black body, and it's given by the Stefan-Boltzmann law. Real surfaces, though, emit less than a black body.
And we measure that difference using emissivity.
Right, emissivity epsilon. It's a value between 0 and 1, indicating how effectively a surface radiates compared to a perfect black body. A shiny mirror might have a very low emissivity, while a matte black surface would be close to 1.
And there's a connection between emitting and absorbing radiation, too.
Yes, Kirchhoff's law of thermal radiation. It basically states that for an object at a given temperature and wavelength, its emissivity is equal to its absorptivity, its ability to absorb incoming radiation.
So good emitters are also good absorbers.
Generally, yes. That's why dark-colored objects tend to get hotter in the sun, they absorb more solar radiation, and they also radiate their own heat more effectively when they're hot.
This must play a huge role in our own comfort.
Absolutely. Think about this. You're standing in a room, and the air temperature is a comfortable 22 degrees Celsius.
Okay.
But it's winter, and the walls are cold, maybe only 10 degrees Celsius. Even though the air is warm, your body will be radiating heat towards those colder walls.
That makes you feel chilly.
It can make a big difference. You could be losing a significant amount of heat, maybe over 150 watts, just by radiation to the cold walls. Now contrast that with summer, when the walls might be 25 degrees. Your radiative heat loss drops dramatically, maybe to only 40 watts.
So even if the thermostat reads the same air temperature, the wall temperature drastically changes how comfortable you feel because of radiation.
Precisely. It's often called the mean radiant temperature, and it's just as important as air temperature for comfort.
And this radiation principle also explains microwaves.
Yes. Microwave ovens are a fantastic example of radiation heat transfer. Unlike a conventional oven, which heats the air first, and then the air heats the food, mostly by convection.
A microwave uses radiation directly.
Right. It generates microwave radiation that penetrates the food and directly excites water, fat, and sugar molecules. This causes them to vibrate rapidly, generating heat within the food itself.
Which is why it cooks so much faster and often more unevenly if you don't stir it.
Exactly. It's heating from the inside out, in a way, thanks to radiation absorption.
So in the real world, these three modes, conduction, convection, radiation, they don't usually happen in isolation, do they?
Very rarely. Usually you have multiple mechanisms at play, especially at surfaces, though maybe not all three within the same medium. For example, inside a solid brick wall, it's primarily conduction.
But the surfaces of that wall.
The surfaces are different. The inner surface might be transferring heat to the room air by convection, and also radiating heat to objects in the room. The outer surface is doing the same with the outside air and surroundings.
So a surface exposed to a fluid and other surfaces can experience both convection and radiation simultaneously.
Definitely. Think about a simple rock sitting outside on a sunny day.
Okay.
It's absorbing radiation from the sun. It's also gaining or losing heat by convection with the surrounding air. And the heat that gets absorbed at the surface is then transferred into the rock's interior by conduction. All three modes are involved in the overall process.
Let's bring it back to us then. A person standing in a room. How much heat are we losing and how?
Okay, let's say you're standing in a room where the air is 20 degrees Celsius and it's a bit breezy. Your skin temperature might be around 29 degrees Celsius.
All right.
You'd be losing heat by convection to the moving air, maybe around 86 watts or so. And you'd also be losing heat by radiation to the surrounding walls and objects, perhaps another 82 watts.
So combined, that's nearly 170 watts.
Roughly, yes. It highlights that both convection and radiation are significant contributors to our heat loss. And, of course, clothing acts as a barrier to reduce both.
This makes me think about something. Why can you stick your hand into a hot oven, say at 200 degrees Celsius, for a few seconds without getting burned? But if you touch a metal pan inside that oven, even if it's only, say, 50 or 60 degrees, you get burned instantly.
That's a fantastic question, and it perfectly illustrates the difference in heat transfer rates.
So it's not just the temperature.
Not just the temperature. Air, especially still air inside an oven, has a very, very low thermal conductivity and a low convection coefficient compared to a solid metal.
So the air doesn't transfer heat to your hand very quickly, even though it's hot.
Exactly. The metal pan, however, has high conductivity. It can dump heat into your hand extremely rapidly upon contact. Plus, in the dry oven air, there might be some evaporative cooling from moisture on your skin, offering a tiny bit of protection. But the main difference is the heat transfer rate due to conduction from the metal versus convection from the air.
That makes sense. Okay, let's shift gears a bit. Are there any really cutting-edge materials related to heat transfer?
Oh, absolutely. One of the most remarkable is aerogel.
Aerogel. Isn't that sometimes called frozen smoke?
That's the one. It's an incredibly lightweight, porous, solid material. It can be up to 99.8% air by volume.
Wow. And what makes it special for heat transfer?
Its structure. It's made of a network of nanoparticles with extremely tiny pores filled with air. This structure gives it an incredibly low thermal conductivity.
How low?
Really low. Some aerogels get down to 0.01 watts per meter Kelvin. For comparison, regular air is about 0.026, and fiberglass insulation might be 0.04.
So it's even better than air at insulating?
In a way, yes. The tiny pores suppress gas conduction and pretty much eliminate convection within the material. And there's very little solid material to conduct heat, either.
What could you do with that?
Imagine replacing a standard glass window pane with an aerogel pane of the same thickness. Glass has a conductivity around 1.0 Weller NK. With aerogel at 0.01, you could potentially reduce the heat loss through that window by a factor of 100.
100 times less heat loss. That's huge for building efficiency.
It's a massive potential impact. Think about energy savings for heating and cooling.
Why aren't our windows all made of aerogel then?
The usual hurdles with cutting-edge materials. Cost and practicality.
Expensive.
Very. The manufacturing process, which often involves something supercritical drying, is complex and costly. And aerogels tend to be quite brittle, kind of fragile.
Like trying to install a window made of smoke, I guess.
Something like that. So making large, durable, transparent panels cheaply is still a major engineering challenge. But research is definitely pushing forward.
So beyond efficiency, understanding heat transfer is also critical for safety.
Absolutely paramount. This ties into an important concept in engineering called prevention through design, or PTD.
What's that about?
It's the idea of designing out hazards right from the start, rather than trying to add safety features later. As engineers, protecting public safety is our primary ethical responsibility.
And in heat transfer, that means preventing burns, fires.
Exactly. Thermal burns are a major concern. Human skin can get a first-degree burn relatively quickly at temperatures around 48 degrees Celsius, and damage becomes almost instant above 70 degrees C.
And that can happen through conduction from touching a hot surface.
Or convection from scalding liquids or hot gases, or even from intense radiation, like from a high-power laser or a fire.
Speaking of fire, heat transfer is key there, too.
Definitely. We need to consider things like the flash point of liquids, that's the lowest temperature where they give off enough vapor to ignite with a spark, and also the auto-ignition temperature.
That's when something bursts into flame on its own without a spark.
Right, just from being hot enough. For example, think about a hot engine surface. Maybe it's exposed to a heat flux, say 5 kilowatts per square meter.
Okay.
If the surrounding air is 40 degrees C, calculation might show that surface could reach nearly 280 degrees C.
And is that dangerous?
It could be. Some lubricating oils have auto-ignition temperatures below that, maybe around 250 C. So if oil leaks onto that hot surface...
You could get a fire spontaneously.
Exactly. So the design solution might be to add insulation to that engine surface to keep its temperature below the auto-ignition point of any fluids that might contact it.
This is where engineering codes and standards must come in.
Absolutely crucial. Organizations like ASME, the American Society of Mechanical Engineers, develop very detailed codes. The famous ASME Boiler and Pressure Vessel Code, for example, originated after a series of devastating boiler explosions in the early 1900s.
So these codes are based on hard lessons learned about safety.
Yes, and they are constantly updated based on new knowledge and technology. They set minimum safety requirements for design, materials, fabrication, inspection.
Can you give an example of how codes apply in a heat transfer context?
Sure. Let's say you're designing a component that has steel plates and uses brass bolts. The code might specify maximum allowable temperatures, maybe 260 degrees C for the steel, and only 149 degrees C for the brass bolts because they lose strength faster at high temperatures.
Okay.
Now, you do your heat transfer analysis, maybe involving some heat flux. Your calculations might show the bolts could reach, say, 249 degrees C.
Ooh, that's way over the limit for brass.
Exactly. And maybe one surface of the steel plate hits 264 degrees C, which is also slightly over its limit. Your analysis analysis immediately tells you this design does not comply with the code. It's unsafe.
So you have to redesign it, maybe use different materials, add cooling, change the geometry.
Whatever it takes to bring those temperatures within the safe operating limits defined by the code. It's a non-negotiable part of the engineering process.
This whole process, the analysis, the codes, it highlights a certain way of thinking, doesn't it? The engineering mindset.
It does. It's very systematic. You start by clearly stating the problem, identifying what you know and what you need to find. You make assumptions, apply the physical laws, like the modes of heat transfer we discussed.
Then you do the calculations, and importantly, you check your answer. Does it make sense?
Right. And part of that rigor involves understanding things like accuracy, precision, and significant digits.
Yes. Accuracy versus precision. They aren't the same thing.
Not at all. Accuracy is how close your measurement or calculation is to the true value. Precision is about how repeatable your measurement is or how many digits you carry in a calculation.
You can be very precise, but completely inaccurate.
Exactly. Like a dart player who throws a tight cluster of darts every time. That's precise, but they're all hitting the outer ring, nowhere near the bullseye. That's not accurate.
And this relates to significant digits.
Yes. It's about honesty in reporting results. If your input measurements, maybe the temperature, the dimensions, are only known to, say, 2 or 3 significant digits,
then your final calculated answer can't suddenly be reported with 6 or 7 digits just because your calculator shows them.
precisely. Your result can only be as precise as the least precise piece of input data you used. Claiming more precision than you actually have is misleading.
It's about reflecting the true uncertainty in the numbers.
Exactly. It's part of careful, responsible engineering work.
Okay, let's bring all this back home, literally, to us. Our own bodies are constantly dealing with heat transfer, aren't they?
They absolutely are. Your body is an incredible biological heat transfer system. It's constantly working to maintain a stable core temperature, right around 37 degrees Celsius or 98.6 Fahrenheit.
And where does our internal heat come from?
From metabolism. All those chemical reactions happening in your cells, breaking down food for energy. Even when you're just sitting still, completely at rest, an average person generates heat.
How much?
Around 84 watts. Think of it like having a small incandescent light bulb running inside you all the time.
And that goes way up when we exercise.
Oh, yeah. During strenuous activity, your metabolic heat production can easily jump tenfold or even more. Your body has to get rid of that extra heat to avoid overheating.
So our feeling of comfort is really about the balance between the heat we generate and the heat we exchange with our surroundings.
It's exactly that balance. And it's influenced by several environmental factors. The air temperature, obviously, most clothed people feel comfortable somewhere between 23 and 27 degrees Celsius.
But it's not just temperature.
No, relative humidity matters too. High humidity makes it harder for sweat to evaporate, which is a key cooling mechanism. So ideally, humidity should be between 30 and 70%. Air motion also plays a role. A breeze increases convective heat loss.
And we felt the effect of radiation earlier, those cold walls.
Right. That's called asymmetric thermal radiation. If one side of you is facing a cold window and the other a warm interior wall, you can feel uncomfortable even if the air temperature is fine, because one side is losing much more heat by radiation.
Our bodies must have ways to cope with these changes, to regulate our temperature.
They do. We have amazing thermoregulation systems. When you get cold, your body tries to conserve heat. Blood flow to the skin is reduced. That's why your hands and feet get cold first.
Trying to keep the core warm.
Exactly. And if that's not enough, you start shivering. Shivering is involuntary muscle contraction, and it can boost your metabolic heat production by up to 6 times, trying to generate more internal heat.
When we get too hot.
The opposite happens. Blood flow to the skin increases, trying to dump heat to the environment. And crucially, you start sweating.
Evaporation is cooling.
Yes, evaporation of sweat from your skin is an incredibly effective way to remove heat. It's so effective that humans can actually survive in environments much hotter than their body temperature, even up to 200 degrees C for short periods. As long as the air is dry enough for sweat to evaporate efficiently and critically, they stay hydrated.
Wow. Our bodies are pretty sophisticated heat exchangers.
They really are. Even the arrangement of blood vessels in our limbs, with arteries carrying warm blood out and veins carrying cooler blood back running close together, creates a countercurrent heat exchange.
How does that help?
It allows some heat from the outgoing arterial blood to transfer directly to the returning venous blood before it reaches the extremities. This helps minimize heat loss from hands and feet in the cold, keeping the core warmer. It's clever biological engineering.
So reflecting on everything we've covered, we've gone from wondering about cooling coffee to the caloric theory, the three modes of transfer, advanced materials like aerogels, safety codes, and all the way to our own bodies.
It's a huge field, but the core concepts, conduction, convection, radiation, driven by temperature differences, underpins so much.
We've seen why heat moves, how it impacts our daily lives, and all sorts of technology.
And also why understanding it is so critical for engineers, not just for making things work efficiently, but for making them work safely.
So, for you listening, what's your next deep dive going to be? How might this deeper understanding of energy transfer maybe inspire you to look at your home's energy use differently?
Or perhaps just appreciate the physics behind why that cold drink stays cold in a thermos, or how your body manages to keep you comfortable.
Understanding these fundamental principles really does equip us to ask better questions about the world.
Absolutely. So keep observing, keep questioning, and keep learning.